most dangerous thing about our sun is its silence. For 9,000 years, it has been calm, unnervingly calm. Calmer than almost every identical star in the galaxy. Scientists recently compared it to hundreds of its closest twins. Every single one of them was more violent. Every single one of them was more unstable. Our sun just sat there, quiet. And no one can explain why. That silence should terrify you. We built our entire civilization during it. Our power grids, our satellites, our hospitals, our economies. All of it calibrated to a sun that might not exist anymore. And we had no idea. This is the story of the star you see every morning, the one you have never truly understood. It is the story of our sun. It's 1965. A chemist named Raymond Davis Jr. steps into a cage elevator at the Homestake Gold Mine in Lead, South Dakota. The cage drops. It falls nearly 1,500 meters into the earth, past rock that is over 1 billion years old, past the silence of a mine that has carved gold from the Black Hills since 1876. When the cage finally stops, Davis steps out onto the 4,850-foot level. The air is warm and still. Above him, almost a mile of solid rock blocks out the sky. This is not where you expect to find someone studying the sun. But Raymond Davis is not looking for sunlight. He is looking for something far stranger. He is looking for ghost particles, neutrinos. They are among the most abundant particles in the universe, and they are almost impossible to detect. A neutrino is so small it makes an electron look enormous. It carries no electrical charge. It passes through solid matter as though it does not exist. Right now, as you watch this, roughly 100 billion neutrinos pass through every square centimeter of your body, every single second. You will never feel a single one. They pass through the walls of your house. They pass through the ground beneath your feet. Most of them pass through the entire planet without touching a single atom. And the source of almost all of them is the sun. Deep inside the sun's core, nuclear fusion converts hydrogen into helium at staggering temperatures. Every second, the sun fuses roughly 600 million tons of hydrogen, and every single one of those reactions produces neutrinos. These particles shoot outward from the core at nearly the speed of light. They reach the sun's surface in about 2 seconds. 8 minutes later, they reach the Earth. They are the only direct evidence of what is happening inside the sun's core right now. Light cannot do this. A photon born in the sun's core bounces between atoms for tens of thousands of years before reaching the surface. The sunlight warming your face today began its journey before modern humans existed. But neutrinos travel straight out. No bouncing, no delay. If you can catch a neutrino from the sun, you are looking at the sun's heart in real time. That is what Raymond Davis wanted to do. And he had a plan. His collaborator was a young theoretical physicist named John Bacall. Bacall had spent years building a mathematical model of the sun's interior. Using that model, he calculated exactly how many neutrinos the sun should produce. And from that number, he calculated how many a detector on Earth should catch. The answer was tiny. Neutrinos almost never interact with anything. To catch even a handful, Davis needed an enormous target, buried deep underground where cosmic rays could not interfere. So he filled a tank the size of an Olympic swimming pool with 100,000 gallons of perchloroethylene, dry cleaning fluid. It sounds absurd, but the chemistry was elegant. Perchloroethylene is rich in chlorine atoms. On the rare occasion a neutrino collides with a chlorine atom, it transforms that atom into a radioactive form of argon. Count the argon atoms, and you count the neutrinos. Every few weeks, Davis would bubble helium gas through the massive tank to extract whatever argon had formed. He was fishing for a handful of atoms in a sea of 100,000 gallons. And in 1968, the first results came back. Bacall's model predicted the detector should capture a specific number of neutrinos. Davis found roughly 1/3 of that number. 2/3 of the sun's neutrinos were missing. At first, everyone assumed someone had made a mistake. The scientific community turned on both men. Independent teams around the world checked and rechecked Bacall's theoretical model. They found no errors. Davis scrutinized every component of his experiment. He tested for contamination. He tested for flaws in the argon extraction. He ran the experiment again, and again, and again. For 25 years, he kept collecting data. The result never changed. Always 1/3. The theorist said the sun should produce a certain number of neutrinos. The chemist said it produced far fewer. One of them had to be wrong. But neither one was. And that was the problem. If the theory was right, and the experiment was right, then something was fundamentally broken. Either the sun was not doing what every model said it should do, or the laws of physics themselves were incomplete. For 33 years, no one could determine which. The solar neutrino problem became one of the most stubborn mysteries in the history of science. It haunted the careers of everyone who touched it. Bacall spent decades defending his calculations. Davis spent decades defending his experiment. Their peers dismissed them, doubted them, and second-guessed them for years. Both men insisted they were right. And the answer, when it finally came, did not just solve one mystery about the sun. It broke open an entirely new understanding of matter itself. But that answer would not arrive for another 3 decades. And when it did, it would come from a nickel mine in Ontario, Canada, 2,000 meters underground, on the other side of the continent from where Davis first lowered his tank into the earth. We will return to it soon, because before we can understand what scientists found at the bottom of that mine, we need to understand what they found at the surface of the sun. And what they found there, in just the last 2 years, has shaken solar physics to its core. On Christmas Eve 2024, a spacecraft the size of a small car did something no human creation had ever done. NASA's Parker Solar Probe flew 3.8 million miles from the surface of the sun, closer than any object built by human hands has ever come to a star. To put that distance in perspective, the Earth orbits 93 million miles from the sun. Mercury, the closest planet, orbits at 36 million miles. Parker Solar Probe flew almost 10 times closer than that. It pierced the corona, the sun's outer atmosphere, and it survived. At its closest approach, the probe moved at 690,000 kilometers per hour. That is 191 kilometers every second. Fast enough to travel from London to New York in under 30 seconds. It is the fastest speed any human-built object has ever achieved, and it needed every bit of that speed. Because at that distance, the sun is trying to kill you. The corona exceeds 1 million degrees. The radiation is ferocious. A carbon foam heat shield less than 12 centimeters thick stood between the probe's instruments and total destruction. Behind that shield, the instruments sat at room temperature, collecting data. And what that data revealed was not what anyone expected. The probe flew through magnetic structures called switchbacks, violent S-shaped kinks in the sun's magnetic field that whip back on themselves like a cracking whip. Scientists knew switchbacks existed. They had detected them before from a distance, but no one predicted how many there would be this close to the sun. Parker found them everywhere. The probe also witnessed something never seen at this resolution. After a massive eruption launched solar material outward into space, blobs of that material reversed course. They fell back toward the sun. The sun was swallowing its own explosions. No model had predicted this behavior. Scientists are still analyzing the data from that single flyby, and Parker has made 26 close approaches so far, with more to come. Each pass rewrites what we thought we knew. But the Parker Solar Probe is not the only reason the sun is making headlines. 12 days before Parker's Christmas Eve flyby, a team at the Max Planck Institute for Solar System Research published a study. It landed like a shockwave. They had spent years analyzing data from NASA's Kepler Space Telescope. NASA originally built Kepler to find planets around other stars. But in doing so, it also recorded the brightness of those stars over time, and brightness fluctuations reveal flares. The Max Planck team examined 56,450 stars that resemble our sun. Same temperature, same brightness, same type. Among those stars, they identified 2,889 superflares. A superflare is not a regular solar flare. It is something else entirely. A superflare releases at least 100 times the energy of the Carrington event of 1859. The Carrington event set telegraph lines on fire across 2 continents. A superflare would make the Carrington event look like a spark. Previous studies estimated that sun-like stars produce superflares once every few thousand years. This study found a very different number. Once per century. 1 superflare per sun-like star, roughly every 100 years. The researchers published their findings in the journal Science on December 13, 2024, and they did not mince words. The Carrington flare released only 1/100th of the energy of a typical superflare. The sun can produce eruptions 100 times more powerful than the worst storm in recorded human history. And stars just like it produce them regularly. Meanwhile, right now, the sun itself is acting strangely. We are in the middle of solar cycle 25. Every major space agency predicted this cycle would be mild. They were wrong. The sun is producing far more sunspots, far more flares, and far more coronal mass ejections than any forecast anticipated. Every time scientists think they understand this star, it proves them wrong. We are living through a golden age of solar science. More spacecraft are watching the sun right now than at any point in human history. And the more data they collect, the more contradictions they find. But before we can understand what Parker's solar probe found inside the sun's atmosphere, we need to return to where we left off, to a gold mine in South Dakota, to a man who spent 33 years insisting he was right. Because the answer to the neutrino mystery did not just solve one problem about the sun, it shattered our understanding of matter itself. We left Raymond Davis underground, 1,500 meters below the surface of South Dakota, counting atoms in a swimming pool of cleaning fluid. For 33 years, his experiment produced the same result. 1/3 of the neutrinos the sun was supposed to send, 2/3 missing. No one could find an error in his detector. No one could find an error in John Bacall's theoretical model. And for 3 decades, the scientific community could not accept what that meant. If both men were right, then either the sun's core did not work the way physics demanded, or the neutrinos themselves did something impossible. The answer came from a nickel mine. In 1999, a new detector called the Sudbury Neutrino Observatory began operating 2,000 meters underground in Ontario, Canada. It differed fundamentally from Davis's experiment. Davis's tank could detect only one type of neutrino. Sudbury could detect all 3. Because here is what no one had understood until then. Neutrinos come in 3 varieties. Physicists call them flavors. There is the electron neutrino, the muon neutrino, and the tau neutrino. The sun's core produces only electron neutrinos, and Davis's chlorine detector could only catch electron neutrinos. So far, no problem. But in 2001, the Sudbury team published their results. They counted the total number of neutrinos arriving from the sun across all 3 flavors. The total matched Bacall's prediction almost exactly. The sun produced precisely the right number of neutrinos. Not a single one was missing. So where had they gone? They had changed. During the 8-minute journey from the sun's core to the Earth, the neutrinos transformed. They shifted between flavors. An electron neutrino would leave the sun. By the time it reached South Dakota, it had become a muon neutrino, or a tau neutrino. Davis's detector could not see those flavors. It was like counting red cars passing through a checkpoint on a motorway. You expect 100. You count 33. For 30 years, you assume the factory is broken. You redesign the factory model. You question the engineers. You recheck the paint orders. Then one day, someone builds a camera that can see all colors, and they discover that the cars are changing color mid-journey. Red becomes blue. Blue becomes green. The factory produced exactly 100 cars. Your checkpoint could only see one color. The factory was never broken. Your understanding of how cars work was wrong. That is what happened with the sun. The sun was never broken. Our understanding of matter was incomplete. Neutrino oscillation, as it became known, meant that neutrinos have mass. The standard model of particle physics had assumed they were massless. It was wrong. Raymond Davis's swimming pool of cleaning fluid had not just solved a problem about the sun, it had broken the standard model of physics. And it all started because one chemist refused to believe his experiment was wrong. In 2002, Raymond Davis Jr. received the Nobel Prize in Physics. He was 87 years old. His health had declined to the point where he could not travel to Stockholm. His son, Andrew, delivered the Nobel lecture on his behalf. Davis had spent nearly 4 decades waiting, doubted by his peers, questioned at every conference, told again and again that his numbers had to be mistaken. He never wavered. He was right. He was always right. He died in 2006 at the age of 91. But the lesson his experiment taught the world has only grown louder with time. The first time we pointed a precision instrument at the sun and asked a simple question, the answer we got back was wrong. Not because the sun had made an error, because we had. And that pattern has repeated with every major discovery since. Everything that follows in this story depends on one thing: the sun's magnetic field. Think of the sun as a ball of superheated gas with no solid surface. It consists almost entirely of hydrogen and helium, so hot that atoms break apart into a soup of charged particles called plasma. This plasma does not rotate evenly. The sun's equator spins faster than its poles. And because charged particles in motion create magnetic fields, This uneven spinning generates a powerful and constantly shifting magnetic force. Imagine stretching a rubber band between your two hands. Now, twist one hand forward and the other back. Keep twisting. The rubber band winds tighter and tighter. It knots, it tangles, it stores enormous tension. That is what happens to the sun's magnetic field. The uneven rotation stretches and twists the field lines until they knot together at the surface. These knots are visible. We call them sunspots. A sunspot is not a blemish or a dark mark. It is a region where a concentrated magnetic field has broken through the surface. The magnetic force suppresses the flow of heat from below, making that patch cooler and darker than its surroundings. Sunspots can be enormous. Some are 10 times the diameter of the Earth. And when the twisted magnetic field lines above a sunspot can no longer hold their shape, they snap. That snap releases energy, enormous energy. Sometimes it releases a solar flare, a burst of radiation that travels at the speed of light. Sometimes it releases a coronal mass ejection, a billion-ton cloud of magnetized plasma hurled into space. And sometimes it releases both at once. This activity follows a cycle. Roughly every 11 years, the sun swings from quiet to violent and back again. At solar minimum, sunspots are rare and the sun is calm. At solar maximum, sunspots multiply and the sun erupts frequently. That same twisting magnetic field drives the cycle. Every 11 years, the field becomes so tangled that it effectively resets. The poles flip. North becomes south. South becomes north. The rubber band unwinds. And then the twisting begins again. Scientists have tracked this cycle since the 1600s. They have built dozens of models to predict it. And yet, right now, Solar Cycle 25 is outperforming every one of those models. The sun is doing more than it should be doing. Again. The neutrino problem took 33 years to solve, but at least it was solved. At least Davis lived to see it. The next mystery on this list has been open for more than 80 years. And despite every spacecraft, every telescope, and every supercomputer we have thrown at it, no one on Earth can explain it. August 18th, 1869. A total solar eclipse crosses the United States. For a few minutes, the moon slides directly in front of the sun, blocking its blinding surface. And in that brief window of darkness, astronomers can see something normally invisible: the corona. The sun's outermost atmosphere, a halo of faint, ghostly light that stretches millions of kilometers into space. During this eclipse, astronomers point their spectroscopes at the corona and split its light into its component colors. They are looking for signatures. Every chemical element produces a unique pattern of colored lines when its light breaks apart. Hydrogen has its pattern. Iron has its pattern. Oxygen has its. In the corona's light, the astronomers find a bright green line. It matches no known element. Nothing in any laboratory on Earth produces this particular wavelength. The conclusion seems obvious. They have discovered a new element. They name it coronium. For 70 years, coronium sits in the scientific record as a mystery element found only in the sun's atmosphere. Textbooks mention it. Papers reference it. No one can reproduce it. Then, in 1939, Swedish physicist Bengt Edlund solves the puzzle. The green line is not a new element. It is iron. Ordinary iron. But iron heated to a temperature so extreme that it has lost 13 of its electrons. For that to happen, the temperature in the corona would need to reach roughly 2 million degrees. And that is where the real problem begins. The sun's surface sits at around 5,800 degrees Kelvin. The corona reaches 1 to 3 million degrees, further from the core, further from the source of all the sun's energy, and yet hotter. The temperature does not decrease as you move away from the sun, it increases by a factor of 300. Imagine standing next to a campfire on a cold night. You feel the warmth on your face. You take one step back, it gets a little cooler. You take another step, cooler still. That is how heat works. That is how heat has always worked. Now imagine taking 10 steps away from that fire, and the air around you suddenly reaches the temperature of a blast furnace, 300 times hotter than the flames you just left. That would violate everything you know about how the universe operates, and yet, that is exactly what the sun does, every single day. The corona should be cooler than the surface. It is not. It is hundreds of times hotter. And for more than 80 years, the best minds in solar physics have tried to explain why. They have two leading theories. The first involves waves. The sun's surface churns constantly, like a pot of water at a rolling boil. This churning motion shakes the magnetic field lines that extend upward into the corona. The vibrations travel along these field lines as a specific type of wave called an Alfvén wave. Think of it like plucking a guitar string. The energy of your finger does not stay where you plucked. It travels along the string. Alfvén waves may carry energy from the turbulent surface upward into the corona, depositing heat far above its origin. The second theory is more violent. The sun's magnetic field lines twist and tangle as the surface churns beneath them. When two tangled lines crowd too close together, they snap and reconnect in a new configuration. This reconnection releases a small burst of energy, a tiny explosion. Scientists call these nanoflares. Individually, each one is insignificant, but the sun may produce millions of them every minute. Millions of tiny explosions, all day, every day. Each one depositing a small packet of heat into the corona. Add them all together, and they might explain the impossible temperature. Both theories are plausible. Both have mathematical support. Both have some observational evidence, and as of today, no one has proven either one. In 2022, NASA's Parker Solar Probe and ESA's Solar Orbiter achieved something remarkable. They measured the same stream of solar wind from two different distances. They found that magnetic switchbacks near the sun deposited energy into the solar wind as it flowed outward. It was the first direct measurement of energy transfer in the region where coronal heating occurs. Scientists called it a significant step forward, but not a solution. The coronal heating problem remains officially unsolved. More than 8 decades after Bengt Edlund revealed that coronium was just impossibly hot iron, no one can explain how the sun heats its atmosphere to 300 times the temperature of its surface. The sun breaks this rule every second of every day. It has been breaking it for 4.6 billion years, and we still do not know how. The neutrino problem shook our understanding of matter. The coronal heating problem shakes our understanding of energy itself. But perhaps the most disturbing discovery about our star is not about what it does. It is about what it does not do. In 2020, a team of researchers at the Max Planck Institute for Solar System Research in Germany asked a deceptively simple question. Is our sun normal? Not normal in the general sense. They did not compare it to red dwarfs or blue giants or dying stars. They compared it only to stars that are essentially identical to ours. Same mass, same surface temperature, same age, same chemical composition, and crucially, the same rotation speed. Rotation matters because a star's rotation drives its magnetic field, and its magnetic field drives everything else. Using data from the European Space Agency's Gaia spacecraft, the team identified 369 stars that met every criterion. 369 near-perfect twins of our Sun. Then, they compared brightness variations. When a star is active, its brightness fluctuates. Sunspots darken the surface, flares brighten it. The more active the star, the more its brightness swings up and down. The results were not what they expected. The Sun's brightness variability was 5 times lower than the average of its twin stars. 5 times. Events like the Carrington event, the worst solar storm in recorded human history, are routine on comparable stars. Our Sun does not behave like its siblings. It is, by every measure, the quiet one. Imagine a classroom of identical twins. Same age, same background, same temperament. Every single one of them is loud, restless, and disruptive. Except one. One twin sits perfectly still at the back of the room, hands folded, eyes forward, not a sound. Now ask yourself, is that twin calm by nature? Or is that twin the one you should be watching most closely? The Max Planck study could not answer that question, but it laid out 2 possibilities. The first is reassuring. Perhaps something about our solar system actively suppresses the Sun's violence. In 2025, researchers at the Helmholtz Center in Germany proposed a mechanism. Venus, Earth, and Jupiter align in a specific configuration roughly every 11 years. That alignment matches the sunspot cycle almost exactly. Their combined tidal pull may act as a kind of pacemaker. It nudges the Sun's magnetic field into a regular, predictable rhythm. And that rhythm may prevent the chaotic magnetic buildup that produces extreme violence on other stars. If this is true, then our Sun is not temporarily quiet. It is structurally quiet, kept in check by the very planets it created. That is the reassuring explanation. Here is the other one. Perhaps the Sun has simply been in a lull. 9,000 years of ice core and tree ring records confirm one thing. The Sun has been consistently mild throughout all of recorded human civilization. Every empire, every revolution, every technological leap our species has made occurred under a calm Sun. But 9,000 years is nothing. The Sun is 4.6 billion years old. 9,000 years is not even a rounding error in its lifespan. It is a single heartbeat. And we know the Sun can behave differently, because it has before. In 1645, sunspots began to vanish. Not gradually, not cyclically. They simply stopped appearing. For the next 70 years, astronomers across Europe recorded almost no sunspots at all. This was not a gap in the data. Astronomers had invented the telescope decades earlier. They were actively watching. The Sun had gone quiet in a way that defied its own 11-year cycle. Scientists now call this period the Maunder Minimum. It coincided with the coldest stretch of the Little Ice Age. Rivers that had never frozen became skating rinks. Harvests failed across northern Europe. The connection between the Maunder Minimum and the Little Ice Age is still debated, but the coincidence is difficult to ignore, and it raises a question that cuts in both directions. If the Sun can go abnormally quiet for 70 years, can it go abnormally loud for an equivalent period? If it can suppress its own cycle, can it also break free of it? The Max Planck researchers chose their words carefully. They said there was no indication of imminent solar hyperactivity. They said the sun had been rather weakly active, even by its own low standards. But they also said this: the sun may have been going through a quiet phase for thousands of years, and we may therefore have a distorted picture of our star. A distorted picture. Every observation we have ever made of the sun may reflect an exception, not the rule. Every model we have ever built may describe a version of the sun that does not represent its true nature. We might be studying the calm twin and calling it normal. And if the sun's calm is not permanent, if it is simply a phase, then every piece of infrastructure on Earth exists for a star that may no longer exist. Every satellite in orbit, every power grid on the ground, every hospital, every airport, every financial exchange, all of it built for the quiet twin. The one sitting still at the back of the room, the one we never thought to worry about. In 1972, astronomer Carl Sagan and his colleague George Mullins sat down with a simple calculation. They discovered a paradox that no one has fully resolved in the 50 years since. The calculation was straightforward. Stars like the sun grow brighter as they age. This is not controversial. It is a well-understood consequence of nuclear fusion. As hydrogen fuses into helium in the core slowly contracts and heats up, producing more energy. Working backward from the sun's current brightness, Sagan and Mullin reached a striking conclusion. 4 billion years ago, the sun was roughly 30% dimmer than it is today. 30% less light, 30% less heat. At that luminosity, Earth's average surface temperature should have sat well below freezing. The oceans should have frozen solid. The entire planet should have been a ball of ice. But it was not. Geological evidence tells a completely different story. Ancient pillow lavas, a type of rock that only forms when molten lava erupts underwater, prove that liquid oceans existed. Tiny crystals called zircons, some dating back 4.4 billion years, carry chemical signatures of liquid water. And most remarkably, fossil evidence suggests that life itself emerged roughly 3.8 billion years ago. Life that required liquid water. Life that required warmth. The sun was too dim to provide either, and yet both existed. This is the faint young sun paradox. The star was too weak. The planet should have frozen. It did not. And we cannot fully explain why. Scientists have proposed several explanations. The leading theory points to greenhouse gases. Early Earth's atmosphere may have held vastly more carbon dioxide and methane, trapping enough heat to compensate for the weaker sun. Volcanoes could have pumped these gases into the atmosphere for hundreds of millions of years. Another theory suggests the moon played a role. 4 billion years ago, the moon orbited roughly 15 times closer to Earth. At that distance, its gravitational pull would have generated enormous tidal forces. These tides would have heated the Earth's interior, adding warmth from below. A third theory points to asteroid impacts. Far more frequent in the early solar system, these impacts could have melted vast areas of rock. The resulting lava lakes could have released massive quantities of warming gases. Each of these explanations contributes something. None of them, alone or in combination, fully resolves the paradox. Climate models still struggle to produce a warm, liquid Earth under a sun that was 30% dimmer. And the problem is not limited to Earth. Mars shows clear evidence of liquid water on its surface during the same era. River channels, modified craters, valley networks. Under a dim sun at a greater distance than Earth, Mars should have been even more frozen. It was not. The faint young sun paradox is not a footnote in the history of science. It is a 4 billion-year-old question about the star that made life possible. And after more than 50 years of study, it remains open. The neutrino problem took 33 years to solve. The coronal heating problem has been open for more than 80. The faint young sun paradox has persisted for more than 50. And the quiet sun anomaly appeared only 4 years ago. Each mystery is different, but they all point to the same unsettling truth. The star we depend on for everything does not work the way we think it does. And that brings us to the question that matters most right now. If the sun can produce violence we have never witnessed, if its calm is an anomaly, if its atmosphere defies the laws of physics, and if it kept a planet warm when the math says it could not, then what happens when it stops being gentle? Let us return to the December 2024 study from the Max Planck Institute, because the number it produced deserves to sit with you for a moment. 56,450 sun-like stars. 2,889 superflares. One superflare per sun-like star, roughly every 100 years. Previous estimates had placed the interval at thousands of years. Some said tens of thousands. This study said 100. The researchers published it in Science, one of the most rigorous peer-reviewed journals in the world. Let us be precise about what a superflare is. The Carrington event of 1859 is the most powerful solar storm in recorded human history. It set telegraph lines on fire. It produced auroras visible in Cuba and Mexico. If it happened today, it would cause catastrophic damage to power grids and satellite systems worldwide. A superflare releases 100 times more energy than the Carrington event. The Carrington event is not the benchmark. It is the footnote. A superflare is to the Carrington event what a hurricane is to a stiff breeze. They are not in the same category. And our sun, according to this study, can produce one. The superflare frequency on sun-like stars follows the same statistical distribution as the sun's own regular flares. The same physics, extended to higher energies. Now, we do not know when the sun will produce a superflare. The study does not make a prediction. No one can. But what we can do is walk through what would happen if one struck Earth. And we should walk through it slowly. Because this is not the Carrington event. This is something else. Start with satellites. Right now, thousands of satellites orbit the Earth. They provide GPS navigation, weather forecasting, military surveillance, internet connectivity, financial transaction timing. A superflare would produce a radiation storm no satellite in orbit can withstand. Many would suffer permanent electronic damage within minutes. Others would lose orbital stability as the upper atmosphere heats and expands, increasing drag. Satellites would begin to fail. Some would go dark. Others would tumble out of control. Within hours, GPS accuracy would degrade or disappear entirely. Weather forecasting models would lose their primary data sources. Military and intelligence systems would go partially blind. That is the first category. It happens within minutes. Now the power grids. When a massive wave of charged particles slams into Earth's magnetic field, it compresses and distorts that field violently. As the magnetic field lines break and reconnect, they induce powerful electrical currents in the ground itself. These ground currents surge through anything conductive running over the Earth's surface. Pipelines, railway lines, undersea cables, and power lines. The transformers that make modern power transmission possible handle alternating current. A superflare would flood them with direct current. The transformers would overheat. Some would melt. Some would catch fire. Some would explode. During the 1989 Quebec blackout, a moderate geomagnetic storm knocked out the entire province's power grid in 90 seconds. A superflare would be 100 times more powerful. High-voltage transformers are not mass-produced. Each one takes 12 to 18 months to manufacture. If enough of them explode simultaneously, there are not enough replacements on Earth to fix the problem. The repair timeline would not stretch days or weeks, it would stretch years. Now, the atmosphere. This is the part that separates a superflare from the Carrington event. A sufficiently powerful superflare would bombard Earth's upper atmosphere with high-energy particles. These particles would trigger chemical reactions that break apart ozone molecules. The ozone layer, the thin shield that protects every living thing from the sun's ultraviolet radiation, would partially disintegrate. Not permanently. Ozone recovers over time, but for months, possibly years, ultraviolet radiation levels at the surface would climb significantly. Crop yields would decline, rates of skin cancer and cataracts would rise. Ecosystems that depend on UV-sensitive organisms, particularly marine plankton, would suffer. The sun would damage the very shield that protects us from the sun. Now, electronics. A superflare would produce not only charged particles, but also an intense burst of X-ray and ultraviolet radiation traveling at the speed of light. This radiation would reach Earth 8 minutes after the flare, far ahead of the slower particle storm. It would ionize the upper atmosphere, causing immediate and total radio blackout across the entire sunlit side of the planet. Aviation communication would cease. Maritime communication would cease. Emergency frequencies would go silent. And on the ground, electromagnetic pulse effects could corrupt or destroy unshielded electronics. Server farms, hospital equipment, banking systems, traffic infrastructure. Digitally stored data could suffer permanent damage. Not deleted, physically altered at the level of individual bits. Financial records, medical histories, government archives, gone. Now, step back. Every system just described, every satellite, every transformer, every server, every hospital, took shape during the 9,000 years of quiet. Engineers calibrated all of it for a sun that behaves the way ours has behaved within human memory. A sun that, as we now know, is 5 times calmer than every comparable star in the galaxy. Our infrastructure does not account for a normal sun. It accounts for an abnormally gentle one, and we built it without knowing the difference. This is not speculation about some distant future threat. The tree ring record tells us it has happened before. Scientists have found at least 5 extreme solar particle events in the past 12,000 years. They discovered them by examining spikes in radioactive carbon preserved in ancient tree rings and ice cores. The most violent of these events occurred around 775 AD. It was roughly 10 times more powerful than the Carrington event, and even that was only 1/100th of a superflare. But here is what makes the tree ring evidence truly unsettling. These records can only capture events where the particle storm hit Earth. The sun erupts in all directions. A flare that misses our planet leaves no trace in any tree ring, no trace in any ice core, no record at all. For every extreme event in the geological record, dozens more may have simply fired the other way. In 2012, the sun produced 2 massive coronal mass ejections. They tore through the exact point in Earth's orbit where our planet had been just 9 days earlier. 9 days. Had the timing shifted by less than 2 weeks, the modern world would have faced a $1 trillion catastrophe. And that was merely a large coronal mass ejection, not a superflare. Not even close. The December 2024 study does not tell us when the next superflare will come. It tells us something worse. It tells us the sun can do it. It tells us stars just like ours do it regularly. And it tells us the only reason we have never experienced one is that we have watched for barely 4 centuries. During what may be the quietest stretch in our star's history, we built everything during the silence. Our grids, our networks, our cities, our economies, our way of life. All of it resting on the assumption that the sun we see today is the sun we will always have. What if it is not? That is the worst case, but it is not the only possible future. Right now, at this moment, the Parker Solar Probe is still flying. It circles the sun every 3 months, passing through the corona again and again. It collects data from a place no human instrument has ever reached. 26 close approaches and counting, each one producing measurements that rewrite what we thought we knew. Scientists are still downloading and analyzing data from the Christmas Eve 2024 flyby, the closest images ever taken of a star, the most detailed readings ever captured of the solar wind at its source. Every pass reveals something unexpected. Every pass raises new questions. And Parker is not alone. ESA's solar orbiter captures the highest resolution images of the sun's surface ever taken. It orbits at an angle that lets it study the poles no previous mission could see. Together, these two spacecraft build a portrait of our star that no generation before ours has ever had. And by 2031, a new mission will join them. ESA's Vigil spacecraft will take up a position where it can observe the sun from the side. Not from Earth's perspective, but from a vantage point that reveals the far side of the sun as it rotates. This means we will see solar storms forming days before they turn toward our planet. For the first time in history, we will have advance warning from an angle the sun cannot hide behind. It will not stop a superflare. Nothing can stop a superflare, but it can give us time. Time to shut down satellites before the radiation hits. Time to disconnect power grids before transformers overload. Time to ground aircraft. Time to protect hospitals. Time to prepare. 30 minutes of warning could save billions of dollars and thousands of lives. Vigil can provide days. And then there is the reassuring possibility. The one raised by the researchers at the Helmholtz Center in Germany. The planetary tidal model. Venus, Earth, and Jupiter aligning every 11 years, pulling on the sun with just enough gravitational force to keep its magnetic field in a steady rhythm. A rhythm that prevents the chaotic magnetic buildup that drives extreme violence on other stars. If this model is correct, our sun is not accidentally quiet. Our planets keep it quiet. The very worlds the sun created hold its violence in check. The sun's calm would not be a lucky phase. It would be a structural feature of our solar system. That has not been proven, but no one has disproven it either. And it offers something rare in this story. Hope grounded in physics rather than wishful thinking. But perhaps the most important thing this video can leave you with is not a reassurance. It is a pattern. In 1968, Raymond Davis found 1/3 of the neutrinos the sun should have produced. For 33 years, no one could explain it. Then, someone built the right detector, asked the right question, and the answer reshaped our understanding of matter itself. In 1869, astronomers discovered what they thought was a new element in the sun's corona. 70 years later, someone identified it as iron heated to temperatures that should be impossible. 80 years after that, we still cannot explain how. But Parker's Solar Probe and Solar Orbiter are closing in. In 1972, Carl Sagan pointed out that the sun should have frozen the Earth 4 billion years ago. 50 years of research have narrowed the answer without finding it. But every decade brings better models, better data, and better understanding. In 2020, the Max Planck Institute discovered our sun is 5 times calmer than its twins. 4 years later, the same institute found that those twins produce superflares once per century. Each of these discoveries began as a contradiction, something that should not be true, but was. Each one humbled the scientists who encountered it, and each one eventually yielded, not to a single genius, but to decades of patient, stubborn, unglamorous work. Raymond Davis spent 33 years counting atoms in a tank of cleaning fluid at the bottom of a gold mine. He was right. He was always right. And the lesson of his life is the lesson of solar science itself. We do not understand the sun. We have never understood the sun. Every century, we understand it a little more, and every time we do, we discover how much more there is to learn. That is not a failure. That is how science works. We call it our sun, as if we know what it is. We do not. We orbit a mystery, and every morning, the mystery rises.